And we can move on. So there's Davide Serradini. He's working at Latvian Institute of Organic Synthesis and will speak about upscaling of synthesis.
Thank you for the presentation. So, we already know a little bit about UMC50. We already see this afternoon. And UMC50 is a diaryl phosphonate which has showed an inhibitory activity against UPR, which was able to prevent damage in dry disease in animal model. And we were asking in Riga to upscale the method, to improve the method of synthesis for UMC50. So how does it work like a process development? We can be divided in three phases. Like we have the evaluation of the process, where we take like the drug discovery process and we see if there is any critical step. Then we start to think like design new synthetic route, which is just making literature screening. And once we decide what kind of route we want to use, we have to optimize any step, any single variable, concentration, temperature, and so on. Here is reported the scheme, which is collected two schemes in once of preparation for UMC50. We have in black the strata that we didn't touch, and condition that we didn't touch that are in common from the drug discovery and the optimized method. In red, we have the condition and reagent used only on the drug discovery phases, while in blue we have the optimized version that we use in Riga to synthesize UMC50. So we will go fast in some steps. Whoops. So we have at the beginning we have a protection to get compound number 3. Then we have oxidation to get Haldad. We have the Bionsinski step to get 5, and then we switched instead to go to compound 6, 7, 8 with this guanylation using this pyrazole activated guanylene compound here. We had on the other side we have like the protection with the hydrochloride and direct guanylation to get our final compound without using a side exchange. The number of steps were reduced from 7 to 5. Over a year, the was increased to 7 to 32, and the atom economy was increased to 10% to 21%. So going deeper in the critical step is like the first we need to protect our 4-aminophenyl alcohol, and the Medchem procedure was just using dioxane with additive like a base, and conversion was good. When I started to work 3 years ago, I just switched to DCM without using any additive, and the conversion was still good. And then a second optimization was to switch to more green solvent like ethyl acetate, and conversion was actually 100% also in that case. The only optimization that we did in this case was on the workup method. We want to avoid any column, any chromatographic separation to reduce the process mass intensity and also the consumption of silica and solvent. And so we decide like we have some color impurity that you can see on the second pictures in the middle, and we use active charcoal, and then we also add a pad of silica, which is kind of a small chromatography that can be used in large scale. And then we discovered that impurity were coming from just one starting material. So when we changed purchase from Apollo Scientific to Fluorochem, actually we were able to avoid the use of charcoal, and just with a pad of silica we have a very nice compound ready for the next step, which is the oxidation to the hydride. In drug discovery, they use Des-Martin pyridine, which is a very gold standard in organic chemistry, and this works very nice. But he has a problem that once has a very bad atom economy, and second, large scale can be a little bit problematic because there is one intermediate in preparation of Des-Martin pyridine which is explosive, and you don't want to end like a multi-kilogram scale, which something can explode out in your hand. So we screen some condition literature, and the tempo is quite used for catalytic oxidation haldane, and there was just a selection of the primary oxidant, which we can select between PDA, air with copper, and sodium hypochlorite. We tested this reaction, and we noted that only sodium hypochlorite and tempo we were having a good conversion. And to purify, we didn't want to use also in this case a chromatographic column, so we use a bisulfite protocol, which in where we precipitate here. We precipitate our compound like in ethanol. You just wash it, then you recover the hydride, and you have a product that can be like to 95 to 99% pure. The optimization was done here like at the beginning, small scale, just understand how much sodium hypochlorite we need using the condition in the protocol finding literature. And then we move to 1 gram scale, but we noted a very poor yield. And with more investigation, we noted that like this ammonium salt is unfortunately is like it over-oxidized the hydroxide carboxylic acid. So just removing that, we were able to double the yield. Then we continue with our optimization, like reducing the amount of potassium bromide and tempo. Then we move to a scale of 8 gram and in the end to a 17 gram. And we were able in the end with the food optimization to get a 71% yield in that multi-gram scale. And also the atom economy was increased to a 33% to a 66%. So the Brzezinski was the bottleneck of the full process. Brzezinski reaction is a condensation between the hydrogen 4, the benzyl carbamate, and the phosphate 2 to generate compound 5. And actually, it's a very straightforward reaction. We have a condensation here to get imine 10. Then we have addition this nucleophile to get compound 5. But what happens in the reaction that we can have the protection from the Lewis acid to get like this free amine and then polymer 12, which is that black color that we see in the reaction. This imine 10 is very reactive, so actually what you have in reaction is only compound 13, which is more stable and it precipitates out. Then we have hydrolysis of the phosphate, which is a consumer like the phosphate, the 3-aryl phosphate to d-aryl phosphate 15, which is a little bit less reactive. And then we have also consumption of the last compound in the reaction medium to get the side product, the hydrolyzed side product. We discovered that adding T-fluoroacetic anhydride in the reaction, we were able to convert the side product 15 to make reactive with the compound 13 and to get the product in order to increase the yield. So with that in mind, we start to optimize. We took the first condition and we noted that with copper we didn't have so much conversion, so we decided to screen Lewis acid that we know that in literature we use for alpha-aminophosphonate synthesis and also we have in-house. And we found that bismuth was actually good and we were able to switch to 11% yield to 31% yield here. So then we start to optimize other conditions like the solvent. We switch to a mix of acetonitrile and THF. With an increase in yield, then in literature we found this 3-fluoroacetic that was actually able to make the d-aryl phosphate react with the aminal, and we were able to have an increase of yield. And then it came out like that we just continued to screen also new Lewis acid, and we found that yttrium triflate was even better than bismuth in the optimized condition. Just using acetonitrile, we were able to have a more than 40% yield. So we start to optimize the yttrium triflate condition, just understanding what kind of concentration we need to use, what kind of quenching time we have to use it. And then we were able to get in a 1 gram scale 51% yield, and then of course that it decreased a little bit when we moved to a 10 gram scale. Furthermore, we note also that Lewis acid not only have ability to make like convert your hydride to product, but they have different ability also to hydrolyze your product. Like we have strong Lewis acid, like titanium tetrachloride, which are very good to convert your hydride, but they're going also to hydrolyze your product 5 there to compound 16. While we have other Lewis acid like yttrium triflate, which are very mild, they are very selective. So you will have like 85% of compound 5 with 50% of compound 16, but you will have also a lot of hydride in the reaction because they are not so strong. While yttrium triflate is in the middle. So it's strong enough to convert your hydride to your product, but it's not strong enough to consume your product. Quenching time was also important. We ran some kinetic experiment here. And we have like here a ratio of products compared to an internal standard and chromatographic concentration. And in orange, we have our product, and we see that we have a peak. So there is a moment where you have to quench the reaction, isolate your product, where you're going to lose it. If you leave just overnight, sometimes you have bad yield. And another things to note that confirm our trifluoroacetic experiment, like that the d-aryl line, blue here also, and light blue here, was above in the case when we don't use trifluoroacetic anhydride, and it was below the line of the product when we use the trifluoroacetic anhydride. It means like that trifluoroacetic anhydride can make this d-aryl react to generate more product. So then we're like, how do we purify this reaction? So at the end of the 8 hours, we have a quite nasty mixture, we can say, and we want to also, in this case, avoid any chromatographic purification. So we develop a method in which we have a basic workup and then a silica powder filtration to get rid of the majority of impurity. Then we have an anti-solvent precipitation in a basic solution of sodium bicarbonate to get rid of any polar impurity. Then we move to a slurry in ethyl acetate acetone to get rid of any apolar impurity. And then in case you need it, you can go to a second slurry to get rid to reach a purity of 99% pure, 99%. So next step was the removal block. In this case, the optimization was quite easy. We just switched from trifluoroacetic acid in DCM to hydrochloric in dioxane, and the only optimization was done on the workup method, where we discovered that depending how much time you leave your slurry, like when you finish the reaction, you solve your compound is some good solvent like ethanol, then you drop it in antisolvent like ethyl acetate, and then you let steering, and the steering time was affecting the purity, and we found that actually 30 minutes at room temperature were able to get us a 97% purity. So the last step of this optimization was like the direct granulation. And we screened on literature how they did, and there was work where they used a scanner deflator, so we want also to see other tool uses, which we have some passion with that, like yttrium bismuth, and they were not able to get the same value of a scanner deflator, but the conversion was still pure with the original condition. So we decided, okay, we have three variables. We have the equivalent of channamide, the time, and the concentration, and the best things to do to screen all these variables in the shortest time is to use design experiment. And differently from Nikos, in this case, we get in contact for the Latvia startup that they develop a software that is based on artificial intelligence that make design experiment for you. So you just set like your design limit, your like the number equivalent, like the minimum or the maximum that you want to test. And it's going to select some random point, then you understand which is the best point. It gets closer and closer until we find like our best condition in this case was to maximize any single variable, because the optimum was on one of the corner of the design and is noted here like in the red zone, where we were able to get like close to 86% yield. So last step is actually how do we purify this chemical. It's still in processing work, and we try actually to crystallized it, but it failed because actually it melted, the compound was not soluble, or it hydrolyzed when we use ethanol. We tried the slurry antisolvent, but also in that case we were not able to increase the purity, and now unfortunately we have to add a column. We have tried to remove any column for the process, but in the end we have to use one. We are investigating reverse phase purification. We have three main impurities. We have some monoryl product here. Then we have the urea that is formed from the granulation in the some presence of water, and then we have some unreactive material there. We tested also our yttrium to generate a serious compound. We did that for a publication that soon will go on RC Advances, and also to generate building blocks. We synthesize all these molecules in multigram fashion from 0.5 up to 3 grams. To test also how much yttrium, how good is yttrium, how good is able to work with some functional group, and some of these molecules can be then modified to make like a bigger chemical space explore, let's say. So then we moved to investigation to other two compounds. So we were asked from Antwerp to make a multigas synthesis of compound 4206, which is a very close analog of UMC50. The only difference that we don't have an aliphatic hydride, but we have aromatic hydride there, and we saw basically 1 carbon less. And we use our protocol that we developed for UMC50. And actually worked very well also in that case. So we have like first a small series of experiments just to understand what time we need to quench, and then what concentration we need to work. Then we have a small set here of proof of concept experiment to show that like working on 0.6 molar with quench 4 hours, so we get the best yield, and then we move like to 1 gram and 5 gram to have like a quite better yield overall compared to UMC50. Second step was, in this case, granulation was done still with the pyrazole, because actually it's not good like in a large scale, but it's like good when you just need to do like once, like few milligrams just for once. And you can easily purify compound 42. And the investigation was done like which kind of salt do we need to use, the chloride or the trifluorocontionium, and which kind of concentration, which kind of solvent. And then we discovered that DCM was better than isopropanol, because with isopropanol we noted these two impurities here, and these two impurities were also noted in the final product, so we're kind of affecting the final purity of a compound. Compound 4207 is still an analog, 4206, but instead to have paracetamol, we have parachlorophenol here. And also in this case, like we start with a small scale experiment here. Then we found like what kind of time we need to use, what kind of concentration. We moved to like proof of concept experiment with isolated yield. And then we just upscaled it, and actually it was working very nice because I believe that this phosphate is much reactive than paracetamol phosphate. In this case, this process requires a little bit of optimization because this molecule is quite reactive in the presence of the base, in this case D pair. It can be hydrolyzed very easily. So we have to work like how to perform that reaction in large scale, because when we move to 1.38 gram and 2.3, we get like a very pure yield, like 11% only. So we decide, okay, we need to first, after TFA DCM, we need to wash with the base solution compound 49 to get rid of any trifluoroacetic acid left in the reaction. And then we need also to wash after the reaction compound 50 with acid solution to get rid of any D pair before putting the compound in the column to avoid any hydrolysis in that. And with that in hand, we were able to go back first to our yield of 40%, and then in a large scale, you got even like more than 60% yield. So there was a good question because we know that UM50 is a racemate, and we need to understand which kind of two enantiomers is more reactive. Actually, in LIOS, like 2 years ago, we were able to separate the two enantiomers. They were then tested in Antwerp, and they were noted that they actually have two different activity, a tenfold difference. And we were trying to develop a stereoselective synthesis of UMC50. So the best way to do is to use a chiral catalyst, and actually also these two people won the Nobel Prize this year in chemistry to develop a chiral catalyst, organic chiral catalyst. So we start to use like first a chiral ligand with our Lewis acid protocol, but we weren't able to have any good yield and any enantiomeric sex. We use proline and ligand 2, which is a derivative of salicylaldehyde. Then we move like to a different kind of reaction called like Kabashny field reaction, which is we isolate amine 10. We use diaryl phosphate, in this case not triaryl phosphate, to generate 5 with a chiral base. In our case was chinconine and quinine, but also in this case we were not able to have any good enantiomeric cess. And then we try still using like the Beyoncé's reaction, but instead to use a Lewis acid with a ligand, we use the camphorsulfonic acid, which has some chirality, but also in this case we failed. So we move for a different strategy that instead to use an enantioselective synthesis for alpha-aminophosphonate, we decide to move to a diastereoselective synthesis of alpha-aminophosphonate. So diastereoisomers have one important advantage, that they can be detected they can be separated in a column, because when you run like an enantioselective synthesis, then you have to isolate your product, and you have to have a purity above 90%, because then you have to use a chiral column to separate the two enantiomers. But with the diastereoisome, you can just use any normal column. So actually you run your reaction, and then you just test it like in the SPSC, and you can see in real time how it's going, like if your catalyst is actually affecting the reaction. So we decide to use a chiral amine here. And what we noted that this chiral amine is already able to give some stereospecificity to one diastereoisome to the other. So we noted like that we have a ratio of 72 to 28, and literature is report a ratio of 75 to 25. So we were asking ourselves like, what if we use a chiral carbamate? Are we able to perform the Beyoncé's reaction and in a chiral fashion? So we screen literature. There is only one work done in the end of the 80s from Japanese people, like that they use like this chiral carbonate, a derivative of menthol and derivative of camphor, and we were able that when you use some bulky chiral carbonate, you are able like to actually make some diastereoisomic cess. So we are still planning, we still have to perform this experiment. What we want to do is like to select a series of commercially available phenol that are, alcohol that are chiral, to convert them to a carbamate and to see if we can insert chirality in the carbon near the phosphorus. And the question is to answer if an amine that is distant 1.47 Armstrong from the anomeric carbon is able to insert a chirality, what we able to do with a carbamate that in our studies is 3.6 Armstrong far. So there is a gap of 2.1 Armstrong between a chiral amine and a chiral carbamate like in the reaction. So that actually is a good question, and we hope like the next month that we will be able to solve. So thank you for your attention, and here for questions.
Okay, thank you, Davide. Cohen has question.
Okay, thank you. And great work. I think Alba can testify how difficult it is to synthesize these compounds on a small scale. And if I see how much effort you have put into upscaling and systematically screening all the conditions to obtain a large amount of the compound, that's a huge and a very nice work. So congratulations with that. I just have one question concerning your last part. So is the idea for the synthesis, for the chiral synthesis, that you use indeed a chiral carbamate and then later on try to cleave that? Or will you use the compounds as such? What's the idea?
No, we can actually cleave it. Carbamate can be cleaved in strong acid condition. My question is if we can apply that for UM50 because we have a Bock protecting group, so that's out of question. We can use a Bock, we can use a nitro halide, then we can use some strong acid. Carbamate can be cleaved because I already did with HBr in acetic acid, so they use a very strong acid actually, and then you can actually insert then the mesyl carbamate with that. But that is a very good question. We want to, for now, just investigate if chiral carbamate can insert chirality, like with some big chiral hydro like cinconine or quinine, and that is the first question. Then if we can cleave it, and then if we can use it for UM50, that are kind of three questions that we want to use. Right.
Okay, any other questions? Okay, maybe I ask you, when you are making this synthesis upscaling method development, how close you consider that you would be for final protocol if you would like to make this in industrial scale?
Yeah. If you want to go to, you need to take into account all the GMP things, and actually we are already thinking to use that. So, for example, we want to use green solvent. That actually they're not really GMP, but some company have like a red list or green list of solvent that they want to use. That's why we switched to DCM to ethyl acetate in our UM50 procedure. And we were thinking also in the hand, we need to analyze the film report to see if we have heteroscandy on them, because then when if you're using transition metal, so actually you need to define if you notice some ppm in the hand. And there is also the reproducibility of that you need to take into account, because when you make a GMP, then you need to repeat your batch, 3 batches in a row, and the yield, the purity should be more or less the same. And we are still investigating, because Bion's reaction is actually a 3-component reaction, which means it's complex and it's also very affected to many variables. It can be room temperature, it can be some water that you have in your starting material, which can affect the reaction. And when you move to GMP, to industrial scale, it's much better in laboratory, because in laboratory I have the humidity of the day can change it from summer to winter, and that can affect the reaction outcome. While in industry level, you don't have that. You can actually work in a closed environment, in a glow box or whatever, so you can actually avoid that. And I believe that in some cases, industrial environment is much better than a lab environment.
Okay, thank you very much, Davide. Nice work.